Hey everyone, welcome back to the Deep Dive. Today we're taking a real plunge into something you might not even know exists, but it's totally fascinating. The Online Encyclopedia of Integer Sequences, or OEIS for short. Imagine a vast, ever-growing library where every book is, well, a list of numbers. And in this library, you discover that seemingly isolated mathematical stories, like, say, the behavior of waves or the ways you can arrange objects, are actually hidden chapters in the same grand mathematical narrative. Today, we're pulling one such remarkable book off the shelf.
And that book is OEIS A000275. It's truly a sequence with a remarkable dual identity. It really showcases how disparate mathematical concepts can converge in elegant and, frankly, surprising ways.
That's what kind of blew me away about this one. On one hand, this sequence perfectly represents the coefficients of a special function, specifically the reciprocal of J0, which is a type of Bessel function, right? Exactly, a key Bessel function. But then, on the other hand, it also counts something entirely different. Pairs of permutations. Pairs with a very specific combinatorial constraint, which mathematicians call rise-arise forbidden.
Right. Rise forbidden. So our mission today is to kind of uncover the precise connections. How do these two seemingly unrelated mathematical realms, the analytical world of special functions, often continuous, smooth, and the discrete world of combinatorics, all about counting and arrangements, how do they come together within this single sequence?
Yeah, and we want to explore what makes A000275 not just important, but, well, in the language of the OEIS, truly nice.
Okay, let's start by just getting a feel for the numbers themselves. The initial terms of A000275 are 1, 1, 3, 19, 2, 11, 3, 6, 5, 1, 9, 0, 9, 2, 1. You can see it. It starts to grow pretty rapidly.
And it's useful to know that the OEIS lists an offset of 0, 3. That simply means the first term we hear, that one ferro, corresponds to A0.
A0, okay.
So this sequence genuinely starts from N00.
It's pretty incredible that this sequence was offered by N.J. Sloan himself and featured in his foundational works like A Handbook of Integer Sequences from 73 and the Encyclopedia of Integer Sequences from 95. What does that tell us about its significance sort of in the bigger OEII picture?
Well, Sloan's personal authorship and, inclusion in those foundational volumes, that immediately signals that A000275 isn't just any sequence. It's considered a fundamental building block. It highlights its early recognition as a significant bridge between different mathematical disciplines, worthy of dedicated study right from the very start of the OEIS project.
All right, let's turn our attention to its analytical side then, the Bessel function connection. When we talk about J0Z, what exactly are we referring to? For someone who might not, deal with them every day.
Sure. J0Z is a Bessel function. Think of Bessel functions as the mathematical fingerprint of things that oscillate or vibrate, usually in a circular or cylindrical way.
Okay.
Like the ripples from a raindrop spreading in a pond, maybe, or the way sound waves behave inside a drumhead. J0Z is the most fundamental of these. It shows up everywhere, from, well, how light bends to how heat spreads in a pipe. It's a real cornerstone of applied mathematics.
And A000275 fits in here how exactly?
So here's the connection. The terms of this sequence are 1, 1, 3, 19, and so on. They are precisely the coefficients you get when you expand the reciprocal of J0Z, that's 1 over J0Z, as a power series.
Wow. So it's like finding this direct, explicit recipe that transforms this continuous analytical function into our discrete sequence of integers.
Precisely. And to truly see this connection, mathematicians use something called an exponential generating function, or EGF. Think of it as a special kind of mathematical packaging that compactly encodes the entire infinite sequence.
Okay, like a formula for the whole sequence at once.
Sort of, yes. And what's amazing is that this EGF, this recipe, is precisely linked to the reciprocal of our Bessel function. It reveals this direct, explicit relationship. The infinite series of our integers on one side, and that continuous analytical function on the other.
It's also mentioned that this EGF has a representation as a continued fraction. What does that hint at? Does that tell us something deeper?
It does. It suggests even more sort of elegant analytical structures underneath. A continued fraction representation often means the function, and therefore the sequence it generates, has very nice or well-behaved properties. It can often be derived from other fundamental mathematical constructs. It's just another layer of elegance in its definition.
And thinking about how fast the sequence grows, 1, 3, 19, 2, 11, it shoots up. There's an asymptotic formula, right, for very large n.
Yes, there is. It essentially tells us that an grows roughly proportional to n factorial squared, which is, extremely fast growth.
N factorial squared, okay.
And the really neat part is that the precise constants in that asymptotic formula, the scaling factor, the base of the exponential part, they are directly connected to the zeros and specific values of Bessel functions themselves.
So it ties back again.
Exactly.
Yeah.
This connection provides really profound insight into the sequence's rapid growth rate. It ties its long-term behavior right back to the very roots of its Bessel function definition. It's a remarkable convergence of analysis and number theory.
Okay, so we've seen how this sequence is intimately tied to the, let's say, smooth, continuous world of Bessel functions. But what's truly mind-bending is that the exact same numbers pop up in a completely different universe, the discrete realm of counting permutations. Let's dive into what pairs of permutations with rise forbidden actually means. Can you break that down?
Okay, sure. So imagine a sequence of distinct numbers, like a permutation, say 1, 3, 2. A rise occurs when a number is immediately followed by a larger number. In 1, 3, 2, there's one rise. The 1 followed by 3. The 3 followed by 2 is a fall.
Got it. 1 to 3 is a rise.
Right. Now, consider pairs of permutations, both of the same length. Let's say we're arranging 1, 2, 3. We say rise forbidden if the two permutations never both have a rise at the same position.
Okay, so if permutation A has a rise between position 1 and 2, permutation B cannot also have a rise between position 1 and 2.
Exactly. They can have rises elsewhere, just not at the same spot simultaneously.
This sounds like something where an example would really help. Let's take a 3, which we said earlier is 19. This means there are 19 pairs of permutations of 1, 2, 3 that have no common rises.
Precisely. And the OEIS entry actually provides a fantastic table to visualize this for N3. Imagine a 6 by 6 grid. Because there are 3 factorials, which is 6, ways to arrange 1, 2, 3.
Okay, 123, 132, 213, 231, 312, 321. Those are the 6.
Right. List those 6 along the top and list them again down the side. Now, each cell in the grid compares the row permutation with the column permutation. The number in the cell tells you how many common rises they have.
Okay, so let's try one. What about the cell where row 123 meets column 123?
Ah, good one. 123 has a rise from 1 to 2. Position 1, and from 2 to 3, position 2. So 2 rises. Since the row and column are identical, they share both rises, so the entry in that cell is 2.
Makes sense. What about row 123 and column 321?
Okay, 123 has those 2 rises. 321 has, well, it only has falls. 3 to 2, 2 to 1. No rises at all, so they can't possibly share any rises. The number of common rises is 0, so the entry is 0.
Right. And the key insight here is?
The key insight, the real aha moment, is if you go through that entire 6 by 6 table and count up all the cells that contain a 0, meaning those pairs of permutations have no common rises, you will find exactly 19 of them.
19, which is exactly a 3.
Exactly a 3. This is a beautiful concrete demonstration of how this abstract combinatorial definition perfectly maps onto our sequence number. It's almost like the sequence itself is winking at you, saying, see, I told you I could do both.
That really does make it click. And this area, counting permutations with forbidden patterns or properties, it's a significant field, right? People like Karlitz, Scoville, Vaughan worked on this.
Absolutely. Their work, often using different generating functions, tailored to combinatorial structures, this time laid a lot of the groundwork for understanding these kinds of enumeration problems. It's a classic example of how different mathematical investigations, starting from seemingly unrelated questions, can converge on the same numerical sequence.
So beyond this amazing dual nature, A000275 has some other interesting, deeper properties. One that caught my eye is the Lucas property. What's that about?
Ah, the Lucas property. It's a fascinating number-theoretic property. It's almost like a secret code embedded within the sequence's arithmetic. It tells you how the terms of the sequence behave when you look at them, modulo a prime number, p.
Okay, modulo p, like the remainder after dividing by p.
Essentially, yes. The property says that to figure out an modulo p, you don't necessarily need to compute the huge number an first. Instead, you can look at the digits of n when written in base p. Let's say n, nk, pk plus o plus n1p plus n0. Then an modulo p is congruent to the product an1, an0 modulo p.
Whoa, so you break down the index n in base p, look up the sequence terms for those smaller digits, multiply them, and that tells you something about the original term modulo p.
Exactly. It reveals this incredible, sort of self-similar, almost fractal-like pattern in the sequence's arithmetic structure. It's a very powerful property when it holds.
That is quite deep. And it also has a recurrence relation, which is often a sign of a well-structured sequence, isn't it?
Yes, definitely. A recurrence relation means you can compute terms based on previous terms. For A000275, for NA0N, can be calculated by summing up combinations of earlier terms, AR, where r goes from 0 to n1, each multiplied by specific binomial coefficients and a mindful one factor. It reinforces that the sequence is well-defined and computable step by step.
And just looking at the OEIS entry, its reach seems even broader. It connects to papers on, let's see, array enumeration, generalized hypergeometric polynomials, even things like tilting modules, inner products.
It truly is a connector. This really underscores how a single integer sequence can act as a nexus, a meeting point, for various branches of mathematics. It highlights these surprising and often profound connections that span seemingly unrelated fields. That's one of the great joys of exploring the OEIS, finding these threads.
So let's recap our deep dive into OEIS A000275. We've explored its really elegant, almost poetic connection to two different worlds. On one side, Bessel functions these fundamental tools in analysis describing physical waves and oscillations, and on the other, a very specific, discrete combinatorial problem, counting pairs of permutations where they can't both have a rise in the same place.
And what this deep dive really emphasizes, I think, is the profound beauty you find in mathematics. Discovering this kind of interconnectedness where abstract functions and concrete counting problems end up reflecting each other, illuminating each other in unexpected ways. It's like finding the same numerical DNA in wildly different mathematical organisms.
It really makes you wonder, doesn't it? What other unexpected links might be hidden within that vast numerical landscape of the OEIS? Perhaps you, our listener, might find your own nice sequence. Maybe by exploring the cross-references listed for A000275, like A212855 or A05133 mentioned in the entry, you can embark on your very own deep dive into the surprising connections hidden in numbers.